Picture this. It's Talladega, 1969. A Plymouth tears past at 199 miles per hour. The car looks like something ripped straight out of a cartoon, a massive wing towering 3 feet above the trunk, a nose cone stretching 2 feet beyond where any normal car would dare to end. The crowd can't believe what they're seeing. This isn't racing anymore. This is something else entirely. This is legacy motoring, and I spend way too much time thinking about the cars that were so fast, so dominant, so utterly revolutionary that the sport itself had to kill them. If you're someone who geeks out over the engineering stories behind the most legendary machines in motorsport history, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Here's the thing. That ridiculous-looking wing wasn't designed by Chrysler's top engineers inside some million-dollar wind tunnel. The breakthrough that would add 30 miles per hour on NASCAR's superspeedways came from a single mechanic working out of a converted gas station. His name was Gary Romberg, and he was about to accidentally revolutionize aerodynamics with nothing but sheet metal, a welding torch, and pure mechanical intuition. Now, you might be thinking, how does a backyard mechanic out-engineer an entire corporation? That's exactly the question. And the answer changes everything you think you know about innovation, racing, and why the most dominant machines in NASCAR history were signed off to die by the very man who built the sport. This is the story of how backyard engineering created the most dominant and most hated race cars in NASCAR history. Cars so fast they rewrote the laws of stock car racing. Cars so controversial that NASCAR's founder personally signed their death warrant. And cars that, after sitting unsold on dealership lots for years, are now selling at auction for over $1 million apiece. Look, to understand why NASCAR eventually declared war on these machines, we need to travel back to 1968, because that's where the desperation that built them began. Ford was crushing everyone. Their Torino Talladega, with its sloped fastback design, was walking away from Chrysler's boxy Chargers and Roadrunners on every track longer than a mile. At Daytona, Ford took 7 of the top 10 spots. At Talladega, they were literally lapping the field. Chrysler was hemorrhaging money and reputation. Their NASCAR program budget was already stretched thin, around $2.8 million for the entire season, roughly $23 million in today's money. Ford was spending nearly twice that. Something had to change, and conventional thinking clearly wasn't going to get them there. Enter Bob Roger, Chrysler's racing chief. He knew the gap couldn't be closed by playing the same game Ford was playing. So he turned to his most unconventional thinker, a mechanic named Gary Romberg, who ran a small speed shop in Detroit. Romberg had been tinkering with aerodynamics in ways that made the formal engineers deeply uncomfortable. While they ran computer simulations and drafted equations on whiteboards, he was bolting sheet metal directly onto cars and watching what happened in the real world. Here's what most people don't realize about that approach. The engineers working in Chrysler's official program were solving a theoretical problem. Romberg was solving a physical one. And at 190 miles per hour, physics doesn't care about your spreadsheet. The first breakthrough came from simple observation. Romberg noticed that at speeds above 180 miles per hour, the rear of the Charger would literally lift off the ground. The car became unstable, unpredictable, genuinely dangerous. Drivers were backing off in sections of the track where they should have been flat out, costing them lap after lap of time. The solution seemed obvious enough. Add downforce to the rear. But the question of how to actually do it was where things got complicated. Romberg started with a simple spoiler, just a strip of aluminum bolted across the trunk. The Charger gained 5 more miles per hour immediately. But at the speeds they were chasing, over 190 miles per hour, it wasn't enough. Not even close. That's when Romberg had what everyone around him initially dismissed as a crazy idea. If a little wing helped, what would happen with a massive one? Working in near secrecy at Creative Industries in Detroit, which was, and I love this detail, literally a converted Sunoco gas station. Romberg and his small team started fabricating. What they built defied every principle of subtlety. The wing stood 23 inches above the trunk lid on the street version. But the race cars ran them even higher, some reaching nearly 3 feet off the body. The vertical stabilizers weren't just structural supports either. They were carefully angled at 45 degrees to provide lateral stability through the turns. The wing alone generated 650 pounds of downforce at 190 miles per hour. To put that into human terms, that's like having 3 full-grown men standing on your trunk lid while you're trying to drive. But here's the engineering genius hiding inside what looked like madness. The wing was mounted directly to the frame rails, completely bypassing the body. The force went straight into the chassis where it was needed, rather than through sheet metal that would have buckled and distorted under that kind of load. But Romberg wasn't even close to done. The Charger's blunt nose was creating a high-pressure zone at the front of the car that acted almost like an air brake, pushing back against forward momentum at speed. Chrysler's engineers had experimented with solutions in their official wind tunnel and achieved what you might call modest improvements. Romberg took a completely different approach. He built an entirely new nose from scratch. The nose cone extended the car by 19 inches. Not just longer in a straight line, but completely redesigned in terms of shape and surface. The headlights were hidden behind vacuum-operated doors that only opened when the car actually needed cooling. The grille opening was reduced to a narrow horizontal slot. Every seam was welded smooth. The final product looked genuinely absurd, like someone had crossed a NASCAR racer with a fighter jet and got the proportions slightly wrong. The engineers laughed when they first saw it. Then they took it to Chelsea Proving Grounds in July of 1969, and nobody was laughing anymore. Charlie Glotzbach, the test driver, couldn't believe what the speedometer was telling him. The car that had been struggling to break 185 miles per hour was suddenly touching 205. The aerodynamic drag coefficient had dropped from 0.58 all the way down to 0.35. That is a staggering improvement that, on paper, should not have been achievable with 1960s technology and a converted gas station as your engineering facility. This is where it gets really interesting, because what was actually happening aerodynamically explains why this car was so special. At 190 miles per hour, a standard Charger was pushing against roughly 950 pounds of aerodynamic resistance. The Daytona, with its nose cone and wing working together as a system, cut that resistance to under 600 pounds. Think about what that means in practical terms. It's the equivalent of removing a parachute from the car mid-race. But the real magic wasn't just in the raw numbers. It was in the balance. The nose reduced front lift by 35% while the wing planted the rear. For the very first time in NASCAR history, a stock car was aerodynamically stable at 200 miles per hour. Not just fast. Stable. That distinction matters enormously because an unstable car at those speeds doesn't just lose time. Kills people. The engines underneath all of this engineering were equally extreme. Under that elongated hood sat Chrysler's 426 Hemi, not the street version that the ordinary buyer could spec out at a dealership, but the full race specification unit. We're talking about 12.5 to 1 compression requiring 103-octane fuel. Dual 4-barrel carburetors flowing 1,450 cubic feet per minute of air. A solid lifter camshaft with 0.590 inches of lift and 320 degrees of duration. The valve springs were wound so aggressively tight that they generated 390 pounds of seat pressure. Most street engines run around 120. In race trim, these engines produced between 575 and 600 horsepower at 6,800 revolutions per minute. Torque peaked at 540 pound-feet at 5,400 revolutions per minute. The rotating assembly was balanced to within half a gram. Connecting rods were X-rayed for stress fractures after every single race. A complete race engine cost $15,000 in 1969, which translates to roughly $125,000 in today's money. Teams went through 3 or 4 of them per season. The first real race came at Talladega, September 14, 1969. Richard Brickhouse won in a Daytona at an average speed of 153.778 miles per hour, a track record that would stand for 4 years. But that average speed number doesn't tell the real story. On the back straightaway, the Daytonas were hitting 200 miles per hour. The closing speeds between the winged cars and everything else on the track were genuinely terrifying to witness from inside a cockpit. Drivers reported passing conventional cars so quickly it felt like the other vehicles were parked stationary, just sitting there as the Daytonas blew by. Plymouth wanted in on the action immediately. Their version, the Superbird, debuted for the 1970 season. It was fundamentally the same concept but built on the Roadrunner platform. The nose was actually even longer at 19.4 inches versus 19 inches for the Daytona. The wing was mounted slightly higher. But the most significant difference between the two cars wasn't about the engineering. It was about production volume, and this is where things get genuinely complicated for Chrysler. NASCAR required manufacturers to produce one road car for every dealership in their network to qualify the model as a legitimate stock car. For Dodge, that meant building 503 Daytonas. Plymouth had a considerably larger dealer network. They had to build 1,935 Superbird. These weren't inexpensive either. A street Daytona stickered at $4,300, roughly $36,000 in today's money. The Superbird came in slightly lower at $4,100. For context, a base Roadrunner cost $2,900. You could buy a perfectly good car for significantly less money. The radical styling, the price premium, the sheer strangeness of what these cars looked like, it all added up to a very difficult sales proposition. On the track, however, nobody was struggling with anything. In 1970, winged cars won 38% of all NASCAR races at speeds exceeding 190 miles per hour. Nothing else could touch them. Pete Hamilton won the 1970 Daytona 500 in a Superbird, lapping the entire field except for the second-place finisher. Buddy Baker set a closed-course speed record at Talladega with a 200.437 mile-per-hour average over one full lap. That record stood completely unchallenged until 1983. These cars weren't just winning. They were making everyone else look like they were competing in a different sport entirely. Here's what most people don't realize about that level of dominance. It doesn't just demoralize your competition. It breaks the economic model of the whole enterprise. Ford and Mercury looked at what Chrysler had built, did the math on what it would cost to match it, and pulled out of NASCAR entirely. General Motors threatened to follow. Attendance at some events was declining. And here's the detail that probably mattered most to Bill France Sr., NASCAR's founder and the man with ultimate authority over the sport's direction. Fans couldn't identify with these spaceship-looking cars. The whole premise of stock car racing, the fundamental appeal that had built the sport into what it was, rested on the idea that what you watched on Sunday reflected what you could buy on Monday. These cars shattered that illusion completely. The good old boys who had built their own machines in backyard shops, who had drag-raced similar-looking cars on country roads, who had felt some genuine connection to what they watched on the track, they were being priced out and alienated by an aerodynamic arms race they could neither understand nor afford to participate in. France faced a genuine crisis. Not just a competitive one, but an existential one for the sport itself. The death sentence arrived in late 1970. For the 1971 season, NASCAR announced new rules with elegant brutality. Any car running aerodynamic aids, meaning wings, nose cones, or specialized bodywork, would be limited to 305 cubic inches of engine displacement. Every other car could run 430 cubic inches. That was a 29% power penalty, dropping output from around 600 horsepower down to approximately 410. The wing cars would be roughly 30 miles per hour slower on the straightaways. They weren't technically banned. They were just made completely uncompetitive, which was a far more efficient way to kill them. Chrysler tried to fight the ruling. They proposed a compromise involving smaller wings and reduced nose cones. France wouldn't budge. His public quote to the press was revealing. The racing should be about drivers, not engineers in lab coat. The irony there was staggering and apparently lost on nobody. The single biggest engineering breakthrough these cars represented had come from a mechanic working in a converted gas station. There wasn't a lab coat in sight when Gary Romberg welded that first wing together. The teams attempted running the cars without their aerodynamic packages for 1971, but it was hopeless. The cars weren't competitive without the aero working as a complete system. Richard Petty switched from Plymouth to Ford. Bobby Allison moved to Chevrolet. The most aerodynamically advanced race cars ever built in America were suddenly obsolete, and the question of what to do with them had no good answers. Many were converted back to standard Chargers and Roadrunners by having the nose cones and wings removed. Some were destroyed in crashes during the final season of their legal operation. A few ended up sitting in junkyards, stripped for whatever usable parts remained. The cultural value of these machines was not yet understood by anyone who had the power to preserve them. Let me frame what that competitive difference actually looked like in concrete terms, because I think the raw numbers are important here. In 1970, a Superbird could lap Daytona International Speedway in 45 seconds flat. A 1971 Plymouth, without the aerodynamic package, needed 48 seconds to do the same lap. 3 seconds per lap sounds like a small number until you understand what it means at racing speeds. That's nearly half a mile of separation after just 50 laps. Over a 500-mile race, the gap becomes catastrophic. The wing cars weren't just faster in some incremental way. They existed in a completely separate performance category, and everyone in the garage area understood that perfectly well. The street cars, meanwhile, were causing their own kind of crisis at dealerships across the country. They weren't selling. The styling was too radical for most buyers. The price premium was too high to justify for a road car that most people would never take anywhere near its limit. Some Daytonas sat on dealer lots for 2 full years without finding buyers. Dealers began making an economic decision that, in retrospect, is heartbreaking. They were stripping off the nose cones and wings and converting the cars back to standard Chargers just to sell them at a normal price to normal customers. One dealer in Illinois buried his entire allocation of nose cones behind his dealership building rather than deal with the storage hassle. Those nose cones were discovered and excavated 30 years later, still intact under the soil. The irony is that those buried fiberglass pieces were likely worth more than the entire original vehicle by the time they were found. Now, you might be thinking the technical story ends there, with the ban and the dealers stripping wings off cars. But here's where it gets really interesting, because the engineering legacy of these machines extends far beyond their brief NASCAR career in ways that almost nobody was talking about at the time. The principle of high-mounted wings creating downforce without disrupting underbody airflow became standard practice in Formula One within a few years of the Daytona's debut. The concept of aerodynamic balance, meaning the precise simultaneous management of both front and rear lift, fundamentally transformed how race car engineers thought about vehicle design at every level of the sport. Even modern production cars, the ones sitting in driveways right now, use active aerodynamic systems that trace a direct philosophical lineage back to what Gary Romberg was figuring out through trial and error in Detroit. Modern NASCAR Cup cars generate approximately 650 pounds of downforce at 200 miles per hour. That number should stop you for a second, because it is exactly what the Daytona's wing was producing in 1969. The difference is that contemporary Cup cars achieve that figure through subtle body shaping, carefully sculpted surfaces, and thousands of hours of computational fluid dynamics work. The Daytona achieved the same number with a wing that looked like it was designed by someone who had never heard the word subtle. The lesson the sport ultimately absorbed was that aerodynamics matter enormously, but they need to be invisible to preserve the fundamental storytelling premise of stock car racing. Here's something that genuinely changes how you think about these cars. In 2007, Chrysler's engineers placed a fully restored Daytona inside a modern wind tunnel equipped with contemporary measuring technology and instrumentation that simply didn't exist in 1969. What they found was remarkable. Gary Romberg's backyard modifications, his intuitive sheet metal work, his trial and error fabrication, had achieved 97% of the theoretical maximum aerodynamic efficiency possible for that basic vehicle shape. Modern CAD software and computational fluid dynamics modeling could improve on his design by exactly 3%. 3%. The man working with a welding torch in a converted gas station had gotten within 3% of what supercomputers would later calculate as the ideal solution. Think about what that actually means. It means Romberg wasn't just a good mechanic with good instincts. He had somehow, through observation and fabrication and a deep physical intuition about how air behaves at speed, arrived at an answer that was essentially correct by any standard you want to apply. The engineers with degrees and wind tunnels and computer models could refine his work slightly at the margins. They couldn't fundamentally improve on it. The technical specifications that emerged from historical research and later analysis make the achievement even more impressive. The angle of attack on the wing was adjustable between 12 and 20 degrees. Teams eventually discovered through on-track testing that 15.5 degrees was the optimal setting for most tracks, steep enough to generate meaningful downforce while shallow enough to keep drag from canceling out the gains. The end plates on either side of the wing weren't functioning purely as structural support. They were managing what engineers call vortex shedding, reducing turbulent airflow behind the wing by roughly 40% and making the entire system dramatically more efficient. The nose cone design incorporated aerodynamic principles that wouldn't be formally described or theoretically understood until computational fluid dynamics became accessible to engineers in the 1980s. The shape naturally created a low-pressure zone underneath the front of the car that pulled air from beneath the body, reducing the front lift that had been making the standard Charger so aerodynamically unstable. The small grille opening slot was precisely sized, whether by calculation or by fortunate accident, to feed the radiator exactly the cooling air it needed without creating excess drag. Every dimension of that nose had been optimized through iteration, through building it and testing it and changing it and testing it again, yet it matched almost exactly what computational tools would determine to be correct decades later. The human cost embedded in this speed record is something the official histories don't always dwell on, but it's important. 3 drivers died during early prototype testing phases before engineers and teams fully understood the aerodynamic forces being generated and how unpredictably they could behave under certain conditions. The closing speed differential between winged cars and conventional cars sharing the track created 11 major accidents during the 1970 season alone. When NASCAR made the decision to effectively ban these machines, it wasn't purely about competitive fairness or fan relatability. There was a genuine survival calculus involved. The speed gap had become a safety problem that had no clean technical solution within the existing framework. But the drivers who mastered these cars before that reckoning arrived became legends in the truest sense of the word. Richard Petty's final truly dominant season came in 1970 behind the wheel of a Superbird. 18 wins. 31 top 5 finishes across 40 races. A level of consistency that the modern era of NASCAR, with its carefully managed competitive balance, is specifically designed to prevent from happening again. Bobby Isaac set 28 international land speed records in a Daytona at Bonneville Salt Flats, including a 217.368 miles per hour average for the flying mile. These weren't just race cars winning oval track events. They were the fastest closed-course automobiles anywhere in the world, competing against the absolute frontier of what was possible. The philosophical question that hangs over all of this history has never fully been resolved. Was NASCAR right to ban them? Look, from a pure business perspective, the answer is almost certainly yes. The sport needed to remain accessible to fans emotionally. It needed manufacturers who couldn't match Chrysler's aerodynamic investment to stay involved. It needed the fiction, or at least the impression, that what people watched on track resembled what they could buy at a dealer. Without those things, the whole enterprise collapses into something much smaller and much less culturally meaningful. But from an engineering perspective, there's a real argument that what happened in 1970 and 1971 was a genuine tragedy. Not in any dramatic sense, but in the specific sense that these cars represented the purest expression of performance over regulation, of innovation over convention, of solving the actual problem rather than the politically acceptable version of the problem. They proved something important about where good ideas actually come from, which is not necessarily from the places with the most resources and the most credentialed people. Gary Romberg looked at air the way you might look at water flowing around an obstacle. He asked a simple question: how do we make the car move through it with less resistance while staying planted to the ground? The answer he arrived at looked ridiculous to everyone who first saw it. It worked at 97% of the theoretical maximum possible efficiency. That gap between how something looks and what it actually does is one of the most consistent features of genuinely innovative thinking across every field you can name. Every race car competing anywhere in the world today uses aerodynamic principles that the Daytona and Superbird pioneered or accelerated significantly. Formula One cars generate more than 5,000 pounds of downforce at racing speed. Indy cars theoretically generate enough downforce at highway speeds that they could drive upside down on a ceiling. Modern NASCAR Cup cars are shaped and refined through thousands of hours of wind tunnel testing and computational simulation. But the conceptual thread that runs through all of it connects back to a mechanic adding sheet metal to a stock car in a converted gas station in Detroit and watching carefully to see what happened next. Here's what I think is the most underappreciated part of this entire story. It's not the speed records. It's not the auction prices, though we will get to those. It's the fact that the Daytona and Superbird existed at a moment of genuine institutional desperation. Chrysler didn't commission a radical aerodynamic program because they had surplus money and ambition to burn. They commissioned it because Ford was destroying them and conventional approaches had failed completely. The innovation didn't come from comfort. It came from necessity, from the specific pressure of being badly beaten with no obvious path back to competitiveness. Romberg's involvement wasn't a planned strategic move either. It was a bet born out of having no better option. When the formal engineers with the wind tunnel access couldn't close the gap on Ford, Roger went to the unconventional thinker who worked on gut instinct and sheet metal. The desperation of that choice is what made the outcome possible. If Chrysler had been marginally competitive, if Ford had only been slightly ahead, the organization would have channeled more resources into the existing approach and refined it incrementally. The Daytona and Superbird never get built. They exist precisely because the situation was bad enough that normal thinking had been set aside. That dynamic desperation unlocking radical innovation shows up throughout automotive history and throughout engineering history broadly. It's rarely the front runner who produces the breakthrough. It's almost always the competitor who has run out of conventional options and has nothing left to lose by trying something genuinely different. The survival story of the cars themselves is equally remarkable and deserves its own moment of attention. Of the 503 Daytonas built for the 1969 and 1970 model years, approximately 385 are believed to still exist today. Given what we know about how these cars were treated immediately after the aerodynamic ban, given the dealers who stripped them and the teams who converted them and the general indifference of the era to preserving what seemed like yesterday's technology, that survival rate is extraordinary. Of the 1,935 Superbirds produced, around 1,000 are estimated to remain in some form. Many are not complete, not numbers matching, not in original configuration. But they exist, which is more than anyone in 1972 might have predicted. The value trajectory of these cars is one of the great automotive investment stories of the past 50 years. The Superbirds and Daytonas that dealerships literally could not sell in 1969 and 1970, the cars that sat gathering dust while dealers begged Chrysler for permission to strip off the distinctive bodywork, those same machines began appreciating once the racing community and the collector car world started understanding what they actually represented. A numbers-matching Hemi-powered Daytona sold at auction in 2023 for $1.43 million. To put that in perspective, the original sticker price in 1969 was $4,300. Even adjusting for inflation, that sticker price translates to roughly $36,000 today. The car sold for nearly 40 times its inflation-adjusted value. Even a 440-powered Superbird in genuinely good condition, not the rarest configuration, brings $200,000 or more at serious collector car auctions. The market has spoken about what these machines represent, and the verdict is that they are worth vastly more than anyone who had the power to save them in 1971 and 1972 could possibly have imagined. Now, you might be thinking the telemetry and data story is done. Here's the thing, it isn't. The revelation that came from examining historical race data more carefully, data that was collected at the time but not fully analyzed until decades later, adds another dimension to understanding why these cars were so thoroughly dominant. The wing cars weren't just faster on the straightaways. They were faster everywhere on the track, and this is a crucial distinction. The aerodynamic stability that the package created allowed drivers to carry significantly more speed through the corners, not just down the straight. Brake zones were shorter because the wing provided meaningful aerodynamic deceleration, giving the mechanical brakes less work to do and allowing later braking points. Tire wear decreased because the downforce was distributed more evenly across all four contact patches, reducing the localized stress that scrubs rubber from tires fastest. The telemetry data from Charlotte Motor Speedway showed winged cars entering Turn 1 at 147 miles per hour. Conventional cars of the same era were peaking at 131 miles per hour in the same corner. That is a 16-mile-per-hour advantage in corner speed. At Charlotte, at Daytona, at Talladega, that advantage compounds itself every single lap because higher corner speed means higher minimum speed throughout the lap, which means the average lap speed is elevated far beyond what straight-line performance alone would predict. This is actually why the cars were so much more controversial than simple top speed would explain. If they had just been faster on the back straight and equal everywhere else, the competitive gap would have been significant but manageable. Because they were faster everywhere, through every corner, under every braking zone, the gap was structural. You couldn't compensate for it with better tire management or superior driving technique. The physics were simply stacked against every other car on the grid. The adjustability of the aerodynamic package gave teams another layer of competitive advantage that's worth understanding. That 12 to 20 degree range of wing angle adjustment didn't just affect downforce levels. It changed the entire handling balance of the car. A steeper angle loaded the rear more aggressively, which helped on high-speed ovals where rear stability was critical. A shallower angle reduced drag on tracks where straight-line speed mattered more than mechanical grip. Teams were essentially able to tune two different parameters simultaneously with a single adjustment, and the teams that understood this most deeply gained an additional advantage on top of the basic aerodynamic superiority the package already provided. The manufacturing story behind the street versions adds one more layer of complexity to an already complicated picture. Chrysler was in an awkward position from the moment NASCAR announced the homologation requirement. They needed to build enough cars to qualify for racing. They also needed those cars to actually sell to real customers at real dealerships. Those two objectives turned out to be almost completely incompatible in practice. The styling that made the Daytona and Superbird so aerodynamically effective also made them deeply polarizing to ordinary car buyers. Most Americans in 1969 and 1970 were not looking for a car with a nose cone extending almost 2 feet beyond the headlights and a wing mounted 3 feet above the trunk. They were looking for muscle, for performance, for a car that communicated speed and power through styling language they already understood. The Daytona and Superbird communicated something genuinely alien to most showroom visitors, and the sales numbers reflected that immediately. There's also a practical issue that historians often gloss over. The nose cone and wing were made from fiberglass, and fiberglass in 1969 was not yet the mature, refined material it would later become. The pieces were fragile by daily driving standard. They collected minor damage in parking lot. They were difficult and expensive to repair. Insurance companies were beginning to pay attention to street cars with documented top speeds above 150 miles per hour and were adjusting premiums accordingly. The combination of radical styling, fiberglass vulnerability, price premium, and insurance complications made these cars a genuinely hard sell even to buyers who found them aesthetically interesting. The options breakdown from original build records tells the story clearly. Of the 503 Daytonas built, only 135 buyers selected the 426 Hemi engine, the option that made the car a true performance machine. Most buyers, to the extent that buyers could be found at all, settled for the 440 cubic inch unit, which was powerful but not the racing specification. Of the 1,935 Superbirds, only 70 left the factory with the Hemi. 70 cars out of nearly 2,000. The car that defined an era of NASCAR domination was, in its street form, mostly purchased by people choosing the less extreme engine option, and mostly purchased reluctantly by dealers trying to clear inventory rather than eagerly by customers who specifically wanted what Chrysler was offering. The contrast between what these cars were on the track and what they were as commercial propositions is one of the defining ironies of the entire story. At Talladega they were invincible. On dealer lots in Ohio and Georgia and California, they were a problem that needed to be solved through pricing discounts and bodywork removal. Now let's close the loop on what all of this actually means, because I think the lesson here is more interesting than a simple story about fast cars getting banned. What the Daytona and Superbird demonstrated, definitively and permanently, is that the relationship between innovation and institution is always adversarial at some level. Every truly significant technological advance disrupts the existing framework. The framework pushes back. Sometimes the advance wins and the framework evolves. Sometimes the framework wins and the advance gets regulated out of existence. In NASCAR in 1970, the institution won. The wing cars were too fast, too expensive, too alienating to the fan base, and too destabilizing to the competitive ecosystem for the sport to absorb them. France had no real choice but to act, and his mechanism for acting was elegant in its indirection. Not a ban, just a displacement limit that made the cars uncompetitive while technically leaving the door open. But here's the thing that I keep coming back to. The institution won the immediate battle and lost the longer war. Every principle that Romberg pioneered in that converted gas station is now standard practice across every form of motorsport. The wing was banned from NASCAR superspeedways, but the thinking behind it propagated through Formula One, through sports car racing, through IndyCar, through every aerodynamic advance that followed. Ideas move faster than regulations, and really good ideas are essentially impossible to suppress permanently. Gary Romberg's specific insight, that you could use a high-mounted wing to plant the rear of a car without sacrificing front-end stability, that you could manage the complete aerodynamic balance of a vehicle through deliberate design, rather than accepting whatever aerodynamics the basic body shape happened to produce, that insight is now so foundational to motorsport engineering that it's taught in undergraduate curricula. It's in textbooks. It's assumed knowledge for anyone entering the profession. The man himself never got the formal recognition that his contribution deserved. The engineers in the wind tunnel laboratories, the ones whose work Romberg's intuitive fabrication had outperformed, they kept their institutional standing and their professional credentials. Romberg went back to running his speed shop. His name appears in the histories of these cars mostly as a footnote, usually described as a mechanic or fabricator, rather than as the aerodynamic innovator he actually was. The 97% efficiency finding from the 2007 wind tunnel study should have rewritten that narrative. I'm not sure it fully has. What you're left with, when you trace this whole story from the 1968 desperation that started it to the 2023 auction that ended one chapter of it, is something that feels genuinely important beyond the world of racing. It's a story about where good ideas actually come from. Not from the institutions with the most resources, not from the credentialed experts with the best equipment, not from the organizations with the biggest budget. Sometimes from a mechanic with a welding torch, a physical intuition about how air behaves at speed, and a problem desperate enough to demand a real solution rather than an incremental refinement of existing approaches. The Daytona and Superbird were a glimpse into an alternate version of racing history where engineering excellence determined winners rather than rulebooks, where the only real constraint was physics rather than politics, where a single person with a genuinely better idea could change everything. That moment lasted approximately 18 months in NASCAR's official history. The ideas behind it never stopped spreading. What's the most radical race car you've ever seen in person? Drop it in the comments below, because I genuinely want to know, and I read more of them than you might think. If you enjoyed this deep dive into the wildest and most consequential era of NASCAR engineering, make sure you subscribe because the next video goes deep into another machine that was too advanced and too controversial for its own time. Until then, keep those engines turning.